The purpose of this lab is to create a computational model that will better approximate the electric force on the charged tapes, given the results of Lab 1 were for a point charge. The model is the same from Lab 1, which is a piece of tape floating above another piece of tape. The physics fundamentals for this lab includes Newton's first law, the idea of electric field and force, and gravitational force. As we recall, Newton's first law means an object at rest remains at rest, and an object in motion remains at motion in constant speed and in a straight line unless acted on by an unbalanced force. For us, this means that the net force is equal to 0. The electric field is equal to kq over r squared in the direction of r hat, where r is the distance between a charged particle and an observation point. And the force on another charged particle by that original charged particle is equal to q times the electric field of the original charged particle. For distributed charges, the electric field is a summation of the charges from each particle, which is usually calculated as an integration. In the end, we found that the computational model required a much larger charge for the distributed charge than for the point charge. For the starting conditions, tape B is stuck to two ends and lying across a gap, and tape A is far enough away to not influence tape B. Here, the system is tape B, and the surroundings are tape A. For the observed values, I inputted my mass, charge, and tape objects from Lab 1. For the electric field function, I calculated the r vector and then used kq over r squared times r hat for the electric field equation. The given line charge function distributes my point charge across an entire line of charges. Finally, this for loop acts as an integration to solve for the electric field of the distributed charges. And here is the resulting simulation. The problem with my code is that the force due to gravity is larger than the force due to the electric field, but they should be balanced. This is because I used the charge from Lab 1, which assumed that the tape was a point charge, but there are many differences that make a distributed charge weaker than a point charge. For example, a distributed charge requires a higher charge density to counteract the force of gravity. Also, the edges of real objects have weaker electric fields than near the center. So through trial and error, I found a charge that would give me a balance of electric force to gravitational force. This charge turned out to have a much greater magnitude than for the initial point charge. So the magnitude was 1.919 e to the negative 9 coulombs, and the assumptions I made were to ignore air resistance and assume each tape had about the same amount of charge that was evenly distributed, and that the net force was 0, as well as that the mass was 8 times e to the negative 6 kilograms. Now, as I said, initially when I modeled it as a point charge, I used a charge of 4.669 e to the negative 10 coulombs, and that gave me unbalanced forces. And like I stated before, real distributed charges have weaker edge electric fields and require higher charge densities to counteract the gravitational force. Therefore, the computational model is most likely to be accurate.